Two charged spheres in equilibrium. Two identical spheres with mass m are hung from silk threads of length L. The spheres have the same charge, Q1 equals Q2 equals Q. The radius of each sphere is very small compared to the distance between the spheres, so they may be treated as point charges. Show that if the angle theta is small, the equilibrium separation d between the spheres is q squared L over 2 pi epsilon 0 mg to the power 1/3, and if theta is small, tangent theta is approximately equal to sine theta. So we can see that we have two identical spheres. They each have the same mass. They each have the same charge q. And isolating one of the spheres here, we can see that there will be a repulsive force due to this charge. There's going to be a tension on this cord, and there's going to be the weight of the sphere pointing down. So we start with drawing a free body diagram of the sphere. Tension makes an angle theta with respect to the vertical axis. Electrical force repulsive in nature is in plus I hat direction. mg, the weight points down. It's in minus j hat direction, as you can see here. Okay, now d is the distance between the spheres. Then we can write the electrical force between the two spheres as F electrical is equal to the Coulomb's constant 1 over 4 pi epsilon 0, the product of the charges Q1, Q2 divided by d squared. And I note that Q1 is equal to Q2 is equal to Q. They have the same charge. Now I can write the net force on the x-axis. The net force on the x-axis is equal to the electrical force pointing in I hat direction minus the tension component on the x-axis, which is t sine theta, minus t sine theta equals to 0. And the total force on the y-axis, on the other hand, I can write here, is going to be t cosine theta in plus j hat direction, mg in minus j hat direction. This is equal to 0. So this gives me two equations. The first equation is for the electrical force 1 over 4 pi epsilon 0 Coulomb's constant, q squared over d squared. The electrical force is equal to t sine theta. At the same time, mg, the weight, is equal to t cosine theta. So if I divide these two equations, I will obtain tangent theta, which is sine over cosine, is going to be q squared divided by 4 pi epsilon 0 mg d squared. So if I look at this triangle here, this d is the separation between the two spheres. So I have distance d over 2 to the central axis. And this forms a right triangle here. So from this triangle, I can read sine theta, which is d over 2l. So I can read that sine theta is d over 2 divided by l, d over 2l. And we're told that this is approximately equal to tangent theta for small theta, for small angles. Therefore, I can write d over 2l tangent theta is equal to q squared over 4 pi epsilon 0 mg d squared. And therefore, we can isolate d here. First of all, I notice that this 2 makes this 4, 2, and I have d. You can see this d square goes here, makes it d cube. So d is going to be equal to the quantity on the right hand side, q squared L goes to the right, Q squared L divided by 2 pi epsilon 0 mg to the power 1 over 3. All right. So we looked at the equilibrium of these two spheres. They each exert an electrical force, repulsive force on the other one. And this is balanced by the tension and the weight. And we can see that the x component of the tension, T sine theta, balances the electrical force. Y component, T cosine theta, balances the weight. The electrical force is 1 over 4 pi epsilon 0, or K, Q squared over D squared, and that's equal to T sine theta. Mg is T cosine theta. Tangent theta, the ratio of these two, is Q squared over 4 pi epsilon 0 mg D squared. And from this triangle here, sine theta is d over 2 divided by L. That's what we see here. That's approximately equal to tangent theta for small angles. So d over 2L is q squared over 4 pi epsilon 0 mg d squared. If we isolate d, we obtain q squared L divided by 2 pi epsilon 0 mg to the power 1/3, which is the suggested answer.